Alright, so today we're going to be talking about kinematics, and in kinematics we have two different types. We have one-dimensional kinematics and we have two-dimensional kinematics. And although two-dimensional kinematics is a little bit more complex, for both types we're going to be using these four big equations for kinematics. And what are these four equations? So let's start off. We have V final, which is a final velocity, is equal to V naught, which is initial velocity, plus acceleration times time. We have V final squared is equal to V naught, which also means initial again, plus 2ax. We have x is equal to x naught, initial distance, plus V naught t plus 1/2 at squared. And finally, we have velocity average is equal to final velocity plus initial velocity over 2. It's important to note that all these equations only work if there's a constant acceleration. So if we have an acceleration that's constant, then we can use these equations. And in kinematics, you're always going to have a constant acceleration, so that's why we're going to be able to use these equations. So let's start an example. So let's say there is a planet, and you are on a spaceship 47.8 kilometers away. And you're currently traveling at a velocity of 323 meters per second. That's very fast if you didn't know. But anyways, the question asks, for you to have a soft landing, for you to land on the planet, let's name it Mars for fun. If you were to land at the planet exactly at 0 meters per second, at what acceleration would you have to be decelerating at, and how long would that take? So with the given variables, we know that we have x, since that's distance. X represents distance, so we have that. We also have our initial velocity. But we also, through our intuition, we know what the final velocity is. Because since we're landing, since we know that we're going to be stopping at the end, we know that our final velocity is going to be equal to 0 meters per second. And then we can look at our equations and basically do some algebra. We're going to look at the variable that we want, acceleration and time. What we want is a and t, acceleration and time. And we're going to find which equation can we isolate one of those equations and plug in our known variables. So let's look at the first one. We have final velocity. We have initial velocity, but we don't have acceleration, nor do we have time, so we cannot use that equation. So our second one, we have final velocity, we have initial velocity, we have our distance, therefore we can use that equation in order to solve for A. But you may be wondering, well, that's solving for final velocity. For these equations, you're going to have to basically solve for each variable, play around with the equation, basically like algebra. Don't confine yourself to these equations. You're always going to have to use these equations to solve a kinematics problem, but it might not be explicitly shown. So if you have to solve for acceleration, you might have to play around with the equation, subtract velocity initial, divide, do whatever you have to do to isolate that variable, to set the equation in terms of that variable. So if we have velocity final squared equals velocity initial squared plus 2ax, we can rewrite that as velocity final squared minus velocity initial squared over 2x, since we divided by 2x, is equal to our acceleration. And now we can plug in numbers. However, before you plug in numbers, you have to make sure that everything is in the standard units, the SI units for physics. And in physics, especially for kinematics, we want to use meters per second, meters, and seconds, respectively, and meters per second squared for acceleration. Now, looking at our variables, this is 0, so it doesn't really matter if it wasn't in standard units. Converting 0 to 0 in anything would be 0. Now, if we have initial velocity, meters per second, good. Our distance is in kilometers, and that's important because if we were to divide meters per second by kilometers, the units would not cancel out, and we wouldn't get the units that we want. So what we want to do is convert our distance into meters, so when we divide meters by meters, they cancel out. So that is an easy fix. There's 1,000 meters in 1 kilometer, so we can rewrite that as 47.8 times 10 to the 3rd meters. Now we're ready to plug into the equation. velocity final is 0 meters per second minus our velocity initial squared, which is 323 meters per second squared, over 2 times 47.8 times 10 to the third meters. And that's going to be equal to our acceleration. So let's plug that into our calculator. And we should get an acceleration of negative 1.09 meters per second squared, remembering that we have three significant figures. So we're going to have to restrict that or round it down. So, some important conceptual stuff to take into account. The reason why we have a negative is because in the equation v final squared minus v initial squared, and we have a negative, obviously. And we're dividing a negative by a positive, so you get a negative. And conceptually, that makes sense. In order for you to go from an initial velocity to 0, you'd have to decelerate, not accelerate. And that's something about kinematics that's really cool. If you have a sign that does not make sense, or you have units that don't make sense, they don't cancel out, you know that you did something wrong, you can look back at your work and find out what you did wrong. And now in order to solve time that it would take, let's look at our equations again. We have final velocity, we have initial velocity, we also have our acceleration. So we could find time by using that equation. And by the looks of it, we could use both this equation and this equation, but it's a lot easier to use this equation than that one. If we were to use that, we'd have to use a quadratic, and we don't want to do that. It's a mess. So we have final velocity is equal to initial velocity plus acceleration times time. So then we have a negative velocity initial, since v final is 0, so you just subtract that over, divided by acceleration is going to be equal to our time. Again, this makes conceptual sense since we have a negative acceleration, a negative initial velocity. Since we moved it over to the left, we should get a positive time. You can't have negative time, so we know we did something right. So that means our time is going to be equal to our initial negative 323 meters per second over our negative 1.90 meters per second squared. And see, meters cancel out and we're left with 1 second, and that's why our units canceled out perfectly. And we should get (296 seconds). So there we have it. We were able to find our variables that we didn't have. We were able to identify the variables that we did have. We found an equation in which we had one unknown variable. We solved for that variable. And yeah, that's basically what kinematics is. Be careful of the negative signs. And this is the very basic example. The next example that we do is going to be a lot more complex. We're going to, not a lot more complex, but we're going to get more and more complex. Alright, so our next example, we're going to imagine that we have a baseball. Beautiful. I'm a great artist, if you didn't know. And let's say that you throw this baseball with an initial velocity of 8.64 meters per second. And you're asked to find how high does that ball go and how long does it take to reach the ground. We're assuming that where you throw it from is the same as where it lands in this example. So we have our initial velocity, and we also have acceleration in this example, because whenever a ball is moving upwards, there is an acceleration due to gravity that is pulling down on the ball, because gravity is a downwards force towards the center of the earth. So now we know that our acceleration is going to be equal to the g constant, which is equal to negative 9.80 meters per second squared. Alright, so in order to find the maximum height that the ball goes at, we can infer that the ball will stop at its maximum height. We know that it will, because whenever the ball reaches its max height, it will stop for a second and then gravity will pull it down. So we know that our max height, we have a velocity of 0 meters per second. So looking at our equations, now we have initial, we have final, and we have acceleration. And we can use this equation, we can also use this equation. And it doesn't matter which equation you use as long as you do it correctly. So let's just use this equation. We have velocity final squared, which in this case would be 0 meters per second, is equal to velocity initial, so let's move that over. We get negative 8.64 meters per second, and we want to divide that by 2 times acceleration. Don't forget your negative for the acceleration due to gravity or deceleration, since it's a downwards force, and that's going to be equal to our height. And remember, x is a variable for distance, so it can be distance in the x or it can be distance in the y. Since we're talking in terms of y, in this case it's going to be distance in the y direction. Since our velocity is in the y direction, we're throwing it straight up, we can assume that our distance is going to be in the y direction as well. So if I wanted to rewrite that equation, it would just be like this. Alright, and we don't have to worry about the variables right now since we're only in the y direction or we're only in the x direction in these examples. So our max height we should get, oh yes, this should be squared, shouldn't it? Yes, this should be squared. We get a maximum height of 3.81 meters. Alright, so we found the height. Now we want to find the time for the ball to go up and come back down. So there's 2 different ways that we can solve this, and I'm going to show you guys the most simplistic way to solve it. What we could do is we could find the time it would take for the ball to reach the height of the maximum height, and then multiply that time by 2. Because we're assuming that we're throwing it from the same position and it's landing at the same height. Therefore, the time for the ball to reach the height of the parabola, since we're assuming it's a perfect parabola, will be the same time it would take for the ball to reach the bottom of the ground. So we're going to look at our equations again, and we realize that we can use this equation in order to find the time at the top of the parabola. So all we'd have to do is, since we know our final velocity is 0, is write, I'll just rewrite it again. We can write negative v initial over acceleration, which in this case would be gravity, is equal to time. So we just divide negative 8.64 by negative 9.80. And we get time as being 0.8816 seconds. But that's to the top of the parabola. We want to find it to the bottom of the parabola, so we multiply that number by 2. You get 1.76 seconds. And there we have it. Alright, so we just basically did algebra again. We found the variable that we didn't have, we plugged in the variables that we did have, and we used intuition. We knew that at the top of the parabola, our velocity would be equal to 0 meters per second. See, sometimes in the problem, that information won't be given. You're going to have to look at it. You're going to have to determine where would the velocity be equal to 0. And you can then plug that into some of the equations and get your answer. And next problem, we're going to be working with a little bit in the x and a little bit in the y direction. And after that, we're going to get into more complex things. Alright guys, so now we're going to get a little bit more complex. We're going to really be thinking about x and y directions a little bit before we go into full-scale projectile motion. So, we have a cliff, and let's say we have a jaguar that jumps exactly horizontally in the x direction. So let's label that as the x-axis. At 34.6 meters per second. That's some crazy jaguar. And the cliff is 15 meters high. Alright? And what we want to find is a distance in the x direction that it travels upon reaching the ground, and the time for it to reach the ground. All right, so now we're going to look at what we have again. We have our initial velocity in the x direction, and we have our height of the cliff, our initial height. Now, let us look at this equation for a second. This is very important. You may be thinking that we're not given acceleration, so we can't use that equation. You are wrong. Because since we're traveling in the x direction, we're using velocity in the x direction if we were using the initial velocity. We rewrite this all in terms of x. So we rewrite it as x equals x naught plus v naught in the x direction times time plus 1/2 at squared. And there is no acceleration in the x direction. The velocity in the x direction remains constant. The only velocity that changes is the velocity in the y direction. Because we have the force due to gravity, which is a negative 9.81 meters per second squared. But in the x direction, there is no x force of gravity. There's only force of gravity pointing down. So our x direction, our velocity in the x direction remains constant. So we have zero acceleration. We can cross that off. And we can basically rewrite this equation as x equals, and since these are, there is no initial and final, we're going to just use x equals v naught x time. We simplify that equation by knowing that our velocity in the x does not change, and therefore we have this equation. But even with this equation, we only have one of the variables. So we're going to have to know another trick, or another important step. If something is traveling horizontally at exactly 0 degrees, if something were to drop to the ground and it to move horizontally, for the time for it to hit the ground is equivalent. So if I were to drop this marker like this, and I were to throw this marker, no matter how hard, exactly horizontally, they would hit the ground at exactly the same time. So with that in mind, we can rewrite this in terms of y, since we're thinking of it dropping. So let's rewrite that equation in terms of y. We have y equals y naught plus v naught t plus 1/2 at squared. All right, and again, since one of these y's is 0, since we're hitting the ground, we can just cross it off. We don't have to worry about it. Now looking at it, we do have acceleration in the y direction, since we were talking about gravity, so we can't cross that off. But our initial y velocity is 0, because when I'm dropping this, or when the leopard, if we're assuming we just drop straight down, it's starting at 0 meters per second. So 0 times 100 seconds or 5 seconds or whatever the time is 0. So we can cross that off. So we've simplified it into y equals 1/2 at squared. And then we can solve this in terms of time. We multiply by 2, divide by a. So we get 2y over a is equal to t squared. Square root that. And we get t is equal to root 2y over a, which we would rewrite as 2y over g, because g is the acceleration in the y direction, which is the gravitational acceleration constant. So now we have time, and once we find time, we can plug that in to find the distance traveled in the x direction. So we have time is equal to root 2 times y, so that's 30, over g, which is 9.81 meters per second squared. And wasn't g negative in the last equation that we used? You're right. But in this example, it is accelerating as it's falling. In the other example with the baseball, as it's moving upwards, it's decelerating because the force of gravity is pulling it downwards. That's why gravity was a negative constant. But in this direction, the velocity is in the same direction as acceleration. That's why we have a positive 9.81 or 9.80. Some people use 9.81 depending on where you are based on elevation, but on AP you use 9.80 meters per second squared. And this makes sense. You can't have a negative of a square root of a negative. That's an unreal number. So conceptually it makes sense, and just looking at the equation should make sense. You shouldn't have a negative. If you have a negative, you did something wrong or you thought of it incorrectly, even though you get the same answer if you converted it back to a positive. So Let's grab our calculator. We're going to plug that in. It would take 1.75 seconds for the jaguar or leopard, I think I changed it like 5 times, to hit the ground at that velocity and that height. Okay, now we have time. We can plug that in there to find our direction the x traveled, since we have our initial x velocity and our time. So we multiply 1.75. And remember, don't round early. I'm keeping the digits in my calculator because you would have early rounding errors and you'll lose points for that. Multiplied by our initial x, 34.6, and we get a distance of 60.5 meters. Alright, so in this problem, it was very important to understand the difference between x and y. Since we were working with initial velocity in the x direction for one of the equations, we were able to know that there is no acceleration in the x direction. However, when we were using our y height, when we were thinking in terms of y, when we were trying to find time for it to drop, we have to use acceleration since acceleration is in the y. So you always have to be thinking about x and y components whenever you're doing some projectile motion. In the next example, we're going to be going at an angle, so it'll get a little bit more complex, but bear with me. Alright, so now we're going to be talking about projectile motion as well. We're going to give another example, but this time it's going to be at an angle. So let's assume that there is a field goal in football, and the football is kicked at a 30-degree angle. That would be theta. Theta is the symbol for angle. And it's kicked at an initial velocity of 32.10 meters per second. And what you have to find is the maximum height and the time for it to hit the ground. Even though that's not drawn as a perfect parabola, you're going to have to assume that it's a perfect parabola because I said so. Alright. So now it's very important to notice that not only do we have an initial velocity in the x direction, we also have an initial velocity in the y direction. In the other example, we were going exactly horizontally. That's why we had no y direction. But in this case, we're having both y and x direction. This is because if I were to throw something at an angle, it's traveling upwards as well as traveling in the x direction. So like that. Get it? So that's why we're going to have to figure out what is our initial velocity in the x direction and in the y direction. So here's how we do it. So you see this triangle right here. You can draw this in terms of vectors. And in order to find the initial velocity in the x direction, we multiply our initial velocity of 32.10 meters per second by cosine 30 degrees. That's for the x. And for the y, we'd multiply the same initial velocity by sine of 30. Why do you do that, you may ask? Well, look at the triangle. Cosine of this angle, cosine theta, which is 30 degrees, is adjacent over hypotenuse. So since this is in the x direction, the adjacent over our initial velocity. That's why we get our x value of the initial velocity by doing that. And similarly for the y, sine opposite in the y direction over our initial velocity. That's why it works. Because think about it. So if we have cosine is equal to x, cosine theta is equal to x over v initial, we just multiply v initial on both sides. So we get x is equal to v initial cosine theta. And the x in this case would be in terms of v initial x, v initial y. Since one of our vectors is velocity, they're all vectors of velocity. Alright, so now that we have that, let's find our initial velocity in the x and our initial velocity in the y. For x, we should get 27.799. I'm going to add some extra digits. So VIX, VIY. You can just divide by 2 because we know that sine 30 is equal to 1/2. If you don't know that, then just plug it into your calculator. It doesn't matter. 16.05 meters per second. And this makes sense. Since it's traveling at a 30-degree angle, which is less than 45 degrees, we know that the x velocity has to be greater than the y velocity. Because, for example, if something were to move, let's say at an 89-degree angle, it's moving a lot more in the y direction than it's moving in the x direction in the same time period. So we know that the velocity in the y has to be much greater than in the x direction. Similarly, if we're at a 30-degree angle, there is a lot more x distance than there is y distance, right? So that's why the x velocity is much greater than the y velocity in this example. Okay, so let's look. One way that we can find the total time for the parabola is by using, we could use this equation actually. Now be careful with the negative and positive signs. This is going to be very important. So let's look at it. We have v final is equal to v initial plus acceleration, but we're talking in the y direction right now. Let's assume that. Plus g, because acceleration in the y is the gravity, times time. Oh, there is no time here, sorry. So looking at it, we can subtract over. We have v final y minus v initial y is equal to g times t. Here's the important thing. Our negative, or our velocity final, is equal to our initial velocity, isn't it? But in the initial velocity, it's positive since it's moving in the upwards direction. Whenever we're speaking in the y direction, if anything moves in the upward direction, that's positive, downwards direction, that's negative. Similarly, with the x-axis, in the right it's positive, to the left it's negative. So in this, because velocity, remember, is not only speed, but speed with direction. The negative and the positive sign represent direction of the speed, and that's what velocity is. So in this, the velocity is positive since moving the y direction, the y velocity is moving upwards. And when it's reaching the final, it's moving in the downwards direction. The v final is downwards, right? That's why this will be a negative number, or the final should be negative since it's in the negative direction. So although they're the same number, we'd get negative 32.10 meters per second minus a positive 32.10 meters per second divided by a negative 9.81 meters per second squared. And that makes sense because negative plus minus a positive is plus a negative divided by a negative is a positive. We get positive seconds, and you can't have negative seconds. So if you didn't flip the sign, what you would have gotten is 32.10 minus 32.10 is equal to 0 seconds. That doesn't make sense. And that's what I'm talking about. You know when you make a mistake in kinematics, usually. So our time is going to be equal to again, 9.81, 9.80. Okay, 6.55 seconds, and I left extra digits in my calculator. So now we have our total time, and that is actually one of the questions that was asked. What is the total time? Now we have to find the maximum height. And since this is a parabola, which we are assuming in our perfect little world is perfect, in that the half or the vertex of the parabola, the time for the ball to reach the vertex, which is the maximum height, is the same as half the time for it to reach the ground, since we're starting at 0 meters and we're hitting the ground at 0 meters, right? So what we can do is, I accidentally erased that. What we can do is assume that the time for the ball to reach the maximum height is half of the time of the ball to reach the ground. So we can just divide our total time by 2. We get t, or we can call it half t total, is equal to 3.2755 seconds. Now, with using that, now we can look at one of these equations. And in order to find maximum height, we want to use an equation that has an x, or in this case would be a y. And by looking at the equations, we see that we can use this equation in order to find our y. So we have y equals y naught plus vy. Remember y, or in terms of y, naught t plus 1/2 gt squared. We get y is equal to vy naught, which is 16.05 meters per second, times our half time of 3.2755. And this is important. Remember, g in this case is acting in the negative direction. Since it's gravity, the acceleration is pulling it downwards when it's trying to reach its maximum height. So the gravity will be negative in this case. So minus 1/2 9.80 times our time squared, which we have right there. Alright, and I could have written plus 1/2 times negative 9.80. I just moved the negative outside. It doesn't matter. So 16.05 times 3.2755 minus 9.80 times 0.5, which is 1/2, times 3.2755 squared. And I got a negative number, so I must have done something wrong. Let's retry it. I must have plugged in something wrong. Times 0.5, 3.2755 squared, and then 16.05 times 3.2755 minus the answer we got for the other. Okay, see, this time I got a positive number, and that's why I'm telling you. I knew I made a mistake, because you can't have negative y maximum distance since we're moving upwards. And we get a height max of 41.8 meters. So in this projectile motion question, it was very important to understand the difference between y components and x components. And basically, we're always using the same 4 equations, but we're using them in different ways. We might have to solve for a certain variable, and remember that in all variables there's x and y components. Sometimes the components are 0. For example, in the cliff question that I asked in the previous example, the y velocity was 0 initially, but in the x direction there was a initial x velocity. And remember, in the x direction, velocity stays constant in projectile motion, since the only acceleration acting is the force of gravity, since we're ignoring air friction in projectile motion. And remember to keep everything in terms of x or in terms of y. So if I use x distance, I have to use x velocity. If I use y distance, I have to use y velocity, and I have to use y acceleration. And if you stick to those, use common sense, make sure you don't make silly errors, projectile motion will be the easiest part of physics that you do.